respected deans, HODs, and other participants, faculty colleagues, and my dear students, a very good afternoon to one and all. This is Josna Devi Bodapati, working as an assistant professor in the Department of CSE, Vignan's Foundation for Science, Technology, and Research. On behalf of the Department of CSE, VFSTR, I welcome you all to this webinar. As you all know, Department of CSE VFSTR has been successfully organizing a series of webinars on the recent research developments for the benefit of the students, faculty, and research scholars. As part of this series, we have so far conducted 4 webinars successfully. The first one was on evolution of artificial neural networks. Then we had another webinar on natural language processing. So later we had one on security in digital payments. And recently we had another webinar on statistical models for speech processing systems. And now it gives me immense pleasure to welcome you all to today's webinar on deep neural networks for sequence-to-sequence modeling by Mr. Dilip Kumar Margam, who is working as a software engineer at Google Bangalore. Coming to the webinar, the talk mainly focuses on the role of deep neural network architectures for sequence-to-sequence learning tasks. Sequence-to-sequence models refer to a family of machine learning approaches used for the applications that expect basically a sequence as input and produces a sequence as output. For example, machine translation, if you consider, the input is a sequence of words in one language, say Telugu, while the output is also another language, which is a sequence of words again in some other language, say French. So that is kind of applications where we can use sequence-to-sequence modeling to represent the task. These sequence-to-sequence models have become quite popular in the recent past and have been widely accepted by the research community. Applications include machine translation, text summarization, speech-to-text translation, and video captioning, etc. So if you observe, Google uses sequence-to-sequence models for machine translation. Recently, Facebook also announced its usage, like the sequence-to-sequence learning usage in solving differential equations. So this talk mainly focuses on various state-of-the-art deep neural networks such as recurrent neural networks, LSTMs, GRUs for modeling the sequence-to-sequence data. So now I request Dr. D. Venkateslu, Professor and Head of the Department CSE, VFSTR, to speak few words on this occasion. Sir, can you please?
Yeah.
Sir.
So thank you very much, Madam. So welcome to Mr. Dilip Kumar Margam, Software Engineer at Google Bangalore. So I'm very much thankful to Mr. Dilip Kumar for accepting our invitation to deliver a talk on deep neural networks for sequence-to-sequence modeling. So I'm sure that this talk is going to be very much useful for our faculty members, researchers across various departments of our university. So I once again thank you very much for your support. I'm sure that all of our faculty as well as the research students are going to learn many things with respect to the deep neural network architectures and their applications to solve various problems that are prevalent in the society. So once again, I'm very much thankful to the organizer, Mrs. Josna Devi. So I welcome Dilip Kumar Margam to start the session. Thank you very much.
Yeah, it's my pleasure. Yeah, I'll start the presentation. I'll start presenting my screen.
Dilip, can you give me a minute? Dilip?
Yeah, sure. Yeah. Hello.
Let me introduce. 1 second. Yeah. Now, thank you, sir, HOD sir, for sharing your views. It's my pleasure to introduce.
Yeah.
Thank you, sir. It's my pleasure to introduce today's speaker, Mr. Dilip Kumar Margam. So he received his BTech and MTech degrees from IIT Madras in the year 2017. Then he joined with the Research and Development R&D Department of Samsung, Bangalore, and worked as a lead engineer research till 2019. Currently, he is working as a software engineer in Google, Bangalore. His research interests include deep learning, speech processing, machine translation, and machine transliteration. He also presented his works at prestigious international conferences like Interspeech and many others. In addition, he filed a patent on method and systems for automatically managing operations of electronic devices recently. So I thank Mr. Dilip for accepting our invitation. Now I invite Mr. Dilip Kumar Margam to take over the session.
Thank you, ma'am. It's my pleasure.
Thank you.
Yeah, I'll start presenting my screen and
Yes,
begin the presentation.
please.
Okay, good evening, everyone. Yeah, so today's topic is going to be on deep neural networks for sequence-to-sequence modeling. Before going into the talk, I want to tell you that today's talk is going to be very basic and easy to understand way. So the main reason I kept the talk in very simple and basic manner or in layman terms is because I was told by Jyotsna ma'am that there'll be wide variety of audience who will be attending this talk, and there could be large portion of audience who are not familiar or have zero or no knowledge on machine learning or deep learning. So today's talk is today's talk will completely be in layman terms with examples and real world applications. So you don't have to worry if you don't know anything about deep neural networks or deep learning, machine learning, anything. What to expect from today's talk? In today's talk, you'll get the intuitive understanding of how things work when it comes to sequence modeling. You'll also understand what are the different type of sequence-to-sequence models that we use in our day-to-day life, and you'll also learn how that modeling works. And you'll learn what is DNN, what is RNN, what is bidirectional RNN, what is encoder decoder model, and what is attention. And you'll also learn why they are required and how they operate. And what you'll not learn is how these models are trained or learned. You'll only learn how these things work, but not how these models are learned. So that can be covered in any other talk, but this talk will be very basic. Yeah, let's begin with a question. Let's see what form of information do we share through internet in our day-to-day life. If we look at that, the most common form of information we share is through images, and the other form is videos. Other thing is text and audio. These four forms of information compose majority of information that we share in internet. There are other forms like GIFs and emojis, but I would say emojis fall under text and GIFs fall under videos. So given that we know there are four forms of information that we share through internet, let's look at audio, video, and text forms. So let's look in more detail what is audio. So here is a sample audio piece where the utterance is, "Did you go to office?" So what is this audio? So audio is a sequence of sounds. When you see like here, the SIL indicates silence sound, then the sound of D, and then the sound of D. So this together becomes did, then you, then and so on the other sounds. So this is audio is if looked in detail, audio is nothing but a sequence of phonemes or sequence of sound. Now let's look at video. Let's look at a small video where Ramdev Baba does Surya Namaskaras. So what is video? Video is a sequence of frames. Here if you look, this is the first frame of the video and so on. The frames comes. This is the second frame, third frame, and so on. Video is sequence of frames. Then let's look at text. Let's consider a text. Did you go to office? So what is this text? This text is sequence of words. Did you go to office. So there's also a question, okay, should this be a sequence of words? It can also be sequence of characters. It can also be sequence of subwords. So it can be anything. That is part of research. Now let's look at real world examples that use this sequence to sequence modeling. Let's look at Google Translate that we use in our daily life. So what does Google Translate do? It takes input text in one language and translate it to other language. Let's look at a small example. So if we give a text in English and ask in English saying how are you, and ask it to translate to other language, say Telugu, it translates it to Miru ela unnaru. Okay, here I am assuming every one of you know Telugu. If not, you can ask me. I can translate it to Hindi or yeah. I mean, I only know Hindi, Telugu, and English. I cannot translate it to any other language.
Dilip, there are audience from other languages also, native speakers of other languages. So now and then you can go.
Okay, so Miru ela unnaru is a Telugu translation of how are you. Yeah, it's a Telugu translation of how are you. This is what Google Translate does. So what is Google Translate here? Google Translate is a sequence to sequence model. It takes input as a sequential input, which is text, and outputs a sequential input, which is text. Now let's look at another application that we come across in our daily life. That is search by voice. So there is this search by voice option when you open a Google homepage. So this search by voice option, what does it do? It takes the input in voice. It takes a voice input and converts it to text as a first thing, and as a second step, it converts text. It searches for the text. So if you look at the first step takes speech and converts it to text. So what is this particular application? So this application is also a sequence to sequence model that takes sequential information as input, which is speech, which is a sequence of phonemes or sounds, and outputs text, which is sequence of characters or words. Next, there is sequence to now I would like to generalize sequence to sequence task. What is sequence to sequence task? Any task which translates an input sequential information to any other form of sequential information is called sequence to sequence task. So what is sequence to sequence model? Any deep neural network model which does this task is a sequence to sequence model. So given that now we know what is a sequence to sequence model and what is sequence to sequence task. Yeah, let's look at how this happens. Let me tell you a fact. Any deep neural network model can only understand numbers. So the input that we give for Google Translate, how are you, is not numbers, right? So what happens here? The first step here is the input sequence is converted to sequence of vectors, which is numbers. How are you is converted to a sequence of vectors and then fed to the Google Translate sequence to sequence model. And similar thing happens with speech as well. Here the input is a sequence of phonemes, which is speech or voice, and even this is converted to sequence of vectors and given to search by voice application. So for any sequence to sequence model, this is the first step. Then what next? Even the output of this model is going to be a vector of sequence of vectors. Then this sequence of vectors is converted to the required format, which is audio or video or text. Let us look first. Let us look at how this conversion happens. How is the input sequence converted to sequence of vectors? The first step. First, let us look at text input. How text input is converted. There are two steps here. First, we define vocabulary, text vocabulary, and then we define mapping. Let's define an example vocabulary. Let's define an example vocabulary. The first word I'm defining is did, then go, view, office, and other common three other common tokens. So end token indicates the end of the sentence. Start token indicates the start of the sentence, and UNK is unknown token. So whenever you see a word which is not present in vocabulary, you map it to unknown. So once you have a vocabulary, you define a mapping. So in our case here, I'm for this example case, I'm defining one hot mapping. One hot mapping is nothing but an array of zeros with only one one. So here, 1 and 6 zeros is a array of dimension 7, which maps to unknown token. Similarly, other one hot embeddings which map to different tokens. So now we define this one hot mappings. So did maps to vector with last element as 1, and so are the other words. So once we define this mapping, we use this mapping in converting the input to the required sequence of vectors. So there are many ways to do this mapping. This one hot mapping is a basic mapping. So there you can also use word to vec embeddings. And the current state of the art uses BERT embeddings and Elmo embeddings and many other embeddings. So what are these embeddings? These embeddings have more meaning in it. For example, if you see one hot embeddings, the embedding of go and did are equidistant to go and you. But when it comes to word to vec embeddings, they have more meaning. Similar words will have closer embeddings, and words with opposite meaning will have like farther embeddings. So now we know how the mapping is done and what vocabulary is. Let's go to step 2, which is tokenization. What happens in tokenization? Tokenization is nothing but we split the text into tokens. Now, for the example sake, let's consider a small input text. Did you go to office? The first step here is we tokenize. So when we tokenize, so here I am tokenizing everything into words. For the sake of this talk, I am assuming tokens as words. There can be character tokens. There can be subword tokens as well. Okay, so now we are assuming words as token. Now I split the input sentence to uh, words. So now we have tokens, which is did you go to office question mark. Now we have the tokens. Now we look for these tokens in the vocabulary. We have did token, we have you token, we have go token in the vocabulary. We don't have to in the vocabulary. Then we map it to unknown. Then we look for office, which is present in vocabulary. Then we look for question mark, which is not present in vocabulary, so we map it to unknown. Once we do this mapping, we take the corresponding embeddings that our mapping defined for. So this is how we get embeddings for the given input text. So given sequential information is converted to sequence of vectors. Now let's go to audio to sequence of vectors. Audio is a sequence of phonemes, as I said. What happens in audio is a 25 milliseconds of window is taken, and that 25 milliseconds of window with that 25 milliseconds of waveform is used to get this MFCC coefficients. So MFCC, if you don't know what these MFCC coefficients, you can think of it as some mathematical formula that you apply on a 25 milliseconds of waveform and you get embeddings. So that you do for all 25 milliseconds of intervals with slide of 10 milliseconds. So once you have these embeddings, you give it to sequence model. Now let's go to video. Same thing with video. First we split video into images, which is frames. Then there are multiple options. One way of getting the vectors is DCT coefficient, or you can use CNN, or you can use ImageNet embeddings. So ImageNet is a very large CNN that is trained on millions and billions of images that's available publicly. So you can use ImageNet and get embeddings for the images from your video and get a sequence of vectors. So once you convert input sequence, which is text, audio, or video, into sequence of vectors, you give it to the model. Yeah. Now let's look at different applications in our day-to-day life that use sequence-to-sequence modeling. So let's consider text-to-text. What are different applications that use text-to-text? First, we have already seen neural machine translation, which is Google Translate, It translates input text in one language to output text in another language. And the second application we see is a chatbot, which is a question answering system like Google Assistant. When you ask a question, which is input text, you get an output, which is output text. Now let's look at audio to text. So audio to text is famously known as speech to text. So it is famously known as automatic speech recognition. So Google Assistant does it. So when you speak to Google Assistant, it converts it to text as a first step. And Google Search by Voice also does it. Video captioning in YouTube also does. So it takes the audio as input and converts to text. And text to audio. Text to audio is known as TTS, text to speech. So even Google Assistant does it. Once it gets a response, it will give the audio response. And this Audible app, which is audiobooks, so it reads out the text present in the books. So that app also does sequence to sequence modeling, where it takes text as input and converts it to audio and interactive voice response. That the response that we get from general customer care numbers. Yeah, let's move forward. The other applications are video to text, video to audio, video to video. So there's audio visual speech recognition, where you view audio plus video and get the text as output. There's visual speech recognition, where only video is given and you get text as output. There's video audio denoising, where you give noisy audio as an input and you get a noise like clean audio as output. Video denoising, where you give video with noise as input and you get a clean video. These are the multiple applications that we use in our day-to-day life, which use sequence to sequence modeling to solve the problem. Yeah. So what do we know till now? We have seen what is sequence to sequence task, where input is sequence and output is sequence, and we have also seen that machine can only understand numbers. So every input sequence is converted to sequence of vectors, and output is also a sequence of vectors, which is converted back to the required sequence format. Yeah. Let's go to the main part of today's talk, which is modeling sequence to sequence task. Okay. Yeah. Let's start with DNN. DNN is a basic deep neural network. So yeah, for those who don't know what is DNN, first let me define what is DNN. Then let us use this DNN to solve a sequence to sequence task and see what happens. So we'll go through this by simple examples. As a first step, let me define what is DNN. Yeah, DNN is a function. You can think of DNN as any function that takes input x and outputs y. So in this case, how do you define DNN? So if DNN is defined as a function with set of matrix multiplications and activation functions. So I have defined a simple DNN with W as a weight matrix and B as a weight matrix. So here what is happening is our input is X and DNN defined is F, W and B. W and B are weight matrices and bias matrices, and F is an activation function, and we get output Y. So what happens is X is multiplied with W and we add the result with B and then apply activation function. For the sake of this talk, let's simplify this even more. Let's make F as identity function. So identity function is nothing but whatever input it gets, it outputs the same thing. So we can, once we define F as identity function, we can ignore F. Now let us also define some arbitrary values to W and B and work on some simple examples to see how a general DNN works. Let's define W as 0, 1, 1, 0 matrix and B as 0.1, 0.1. Yeah, so this is not actually a deep neural network because it's not very deep. It's only one layer with only 2 hidden units. So since the dimension is 2, it's only 2 hidden units. Now let's work on a small example. Let's use this DNN to translate English to Telugu. This is the task. We are trying to translate any word in English to any word in Telugu. As we have defined in the previous slide, our DNN is Wx plus B, where X is the input and W is the weight matrix and B is the bias matrix, and F is identity function. The first step in any translation task, as I have defined earlier, is defining vocabulary and mapping. So first, let us define vocabulary. Here, since we have two languages, one English and Telugu. First, let's define vocabulary for English. So I am defining a very small vocabulary of only two elements. So one first word is bank. I am mapping it to 0.2, 0.7. And second word is river. I am mapping it to 0.4 and 0.6. This is our English vocabulary. Then let me define our Telugu vocabulary. So the first word in the Telugu vocabulary I am defining is bank, which maps to 0.8 and 0.3. And the second word is nadi, which maps to 0.7, 0.5. Now, as we have defined vocabulary as a first step, what is the second step we do? Let's try to use this DNN to translate English word bank to Telugu. Let's see what happens. We have the input bank. Then what we do, we look at vocabulary and get the corresponding mapping, which is 0.2, 0.7. Once we get corresponding mapping, which will be X, we give it to DNN, which is a function of Wx plus B. So we do this Wx plus B matrix multiplication and addition to get our output, which is 0.8 and 0.3, which will be our Y. So once we get our Y, we look at output vocabulary and see which is it, like what does it map to. Here 0.8 and 0.3 maps to bank. So yeah, this DNN work like magic. It's able to translate input bank, which is in Telugu, which is in English, to bank in Telugu. Now the question might be, how do you get this right W and B matrices? So yeah, this right W and B matrices are obtained by training a DNN, which is not covered as part of this talk, to keep this talk as a very basic talk. So yeah, we have to train DNN to get correct values for W and B. Let's look at other examples now. Let's try to translate river to Telugu. Yeah, river as input we have. We look at English vocabulary and get the embeddings for river. Then we give it to DNN. Then what we do, yeah, then DNN outputs 0.7, 0.5. Then we look for 0.7, 0.5 in our output vocabulary, Telugu vocabulary, which maps to nadi, and it gives output nadi. Yeah. Okay. Now we have worked out two examples, which is bank from English to Telugu and river from English to Telugu. River from English to Telugu, which is nadi. Now let's look into more details. Let's use the same DNN to translate the phrase. Let's translate a phrase river bank to Telugu. Yeah, so if you don't know okay. Let's translate river bank to Telugu. The first step we do is tokenize, which is we split river bank into two words, which is going to be river and bank. Now we have two words, river and bank. First, we give river to the DNN, we get nadi. So if you don't know Telugu, nadi is a translation of river. So in Hindi, it is nadi only. Yeah. Next, we go to second word, which is bank. We translate bank to Telugu, which came out as bank. Now, yeah, is this what expected? What is the correct translation of river bank to Telugu? It's not nadi bank, right? It is nadi oddu. Nadi ka kinara in Hindi. So nadi oddu. So what happened here? Why did DNN fail? The issue, if you see why DNN failed, DNN is failing to take the past input into consideration while trying to predict the current output. So when it is trying to predict bank in Telugu, it has to know that it has seen river previously. So it is not that English bank where money is stored, but this bank refers to Oddu, which is Kinara in Hindi. Yeah. So that information we have to somehow pass to this DNN so that it will do the correct prediction. So the solution here is drawback is it fails to see the past context. The solution is RNN, which is a recurrent neural network. Let us see what recurrent neural network does. What is RNN? So RNN is very similar to DNN. So if you see the DNN is y is equal to f of wx plus b, right? So what is RNN? RNN is also same thing. Y is equal to wx, which is present in DNN, plus b, which is also present in DNN. But there is this past context term. What is this? It is w into y t minus 1. What is t minus 1? It is the output, previous output. So basically this w into y t minus 1 is a past context that we are giving to RNN. This is the way we are saying RNN, that we have seen these words in the past, so the prediction could be different. So let's see how it happens in the example in the diagram. So when river is given to RNN, it will predict Nadi. And the second is bank. So for bank, when it tries to predict bank, it will also take input from past output, which is yt minus 1. So this blue arrow indicates the past context, and this bank is the current input. When these both are given, it will predict the right output, which is Nadi Urdu. So this is how RNN is able to predict the right output by considering the past context, which is Nadi Urdu, when river bank is translated to Telugu. In Hindi, it will be Nadi ka Kinara, Nadi Kinara, probably. Yeah. Let's go. Let's try different. Let's try different example now. Yeah, let's give Amma as input. Amma means mother in Telugu. So let's give Amma as input. It gives mother as output. That's very good. Now let's give Rajshekhar as input. It gives Rajshekhar as output. So if you know, if you watch Big Boss in Telugu, Amma Rajshekhar is one of the contestant in Big Boss, and is also a director and a choreographer in Tollywood and Tamil industry as well. So yeah, Amma Rajshekhar is a name where Amma is a surname. So when you use RNN to translate Amma Rajshekhar to English, it translates it to Mother Rajshekhar. But the correct translation is Amma Rajshekhar. Why is it failing? So if we have such RNN model, can we launch it to the real? Can we launch it to the real world? No, right? So it fails. So where is it failing? It is failing to see the future context. What comes next? So if we somehow able to give the future context, put future context in this RNN, I think we can get the right prediction. So drawback is RNN fails to see future context to predict mother for input Amma. Yeah, let's see how we can solve this drawback. Solution is bidirectional RNN. Yeah, let's see what is bidirectional RNN. Yeah, bidirectional RNN is basically two RNNs. One is forward RNN. Forward RNN is same thing that we have seen earlier, where Amma is given and mother is predicted, and then Rajshekhar is given, Rajshekhar is predicted. Now there is another RNN which is called backward RNN, which takes input in backward order. So first it takes Rajshekhar as input, then predicts Rajshekhar, and then it takes Amma as input and predicts Amma. So now given that it has context from forward and backward, it's able to predict the right output. So that is what I have written here. Bidirectional RNN considers context from both directions, past and future. And yeah, bidirectional RNN consists of two parts. One is forward RNN and other is backward RNN. Now we are not going to look into how this model is trained, but we are only looking at how the model works in real world. Yeah, let's go to next example. Let's consider longer sequence. Like let's consider this sentence. Lord Rama went to Lanka and killed Ravana to save his wife. Now the question is, what does his refers to? His refers to Rama, right? But sometimes it happens that Aranan thinks his refers to Ravana. So why? So this is seen generally. So RNN performs poorly on longer sequences. RNN fails to capture long-term dependencies. So what is the solution? The solution here is LSTM, long short-term memory networks, and gated recurrent units. Yeah, here I want to add a small disclaimer. The real motivation for coming up with LSTM or GRU is a vanishing gradient problem, which is observed while training RNN. But that vanishing gradient problem is going to be out of the scope of this talk, so I won't be discussing about it. Yeah, let's go ahead and see what is LSTM. What is LSTM, long short. So the full form of LSTM is long short-term memory. So the main part of LSTM is memory cell that stores the already seen context in it. So and it's LSTM is also a RNN. So it takes two things as input. One is the actual input at current time step, and the output from the previous time step, which is output of t-1. So it takes two things as input. The first component of LSTM is input gate. What does input gate do? Input gate tells which input is important. For example, there are certain words in English like the, a, and etc. like other stop words which are not important. In such cases, input gates doesn't allow it to pass. So input gate tells which input should be passed to the cell. Next, there's other thing called forget gate. So forget gate tells which input to which when to forget the existing context. So there are cases where we want the existing context to be forgotten. For example, when a sentence or if a paragraph is complete, we may not want it. So when RNN LSTM can know when to forget, and forget gate tells when to forget. Next comes output gate. Output gate tells when to output. So the composition of input gate, forget gate, and output gate is nothing but LSTM cell. Now the question comes over here is, how does this gates know when to forget or when to accept? So my answer would be we train the right weights to it. That is part of training, and also these gates also consider the input and the previous output as one of their inputs to consider which input to be forgotten or which input to be accepted. So this is what LSTM is. Because LSTM has this memory cell and all these gates, it's able to remember longer context and do well for longer sequences. Let's go ahead and see what is GRU. So GRU in simple terms is a LSTM without output gate. So GRU is same as LSTM without output gate. People have observed that output gate is not adding much value in the final results, and removing output gate is beneficial in two ways. One is number of computations reduces, and it also shown good or almost similar performance as LSTM. Yeah, GRU, the difference between GRU and LSTM is GRU has only 2 gates and LSTM has 3 gates. Now let's try to solve another problem. Yeah, let's consider input మీరు ఆఫీస్కు వెళ్ళారా. Okay, this input let's try to translate it into English. So మీరు ఆఫీస్కు వెళ్ళారా is a Telugu word which Telugu sentence which means have you gone to office or did you go to office. Yeah, let's see what does an RNN do. So here RNN can be LSTM or GRU as well. RNN is a very generic term, so when you say RNN it can mean LSTM or GRU as well. So it takes Miro as input and outputs U. Then Yeah, the next thing is office school. Then it predicts office. So office school is predicted as office, Miru is predicted as you, and the next word is Velara, which is predicted as went, and question mark is predicted as question mark. So the translation of Miru office ku Velara came out to be you office went. So it is kind of broken English that I used to speak when I was kid. Yeah. So what are the constraints here? Why is this the case? Let's look into more details. What is happening here? So the actual output is supposed to be did you go to office? If we look into more details, input is of length in, of length 4. It has 4 tokens: Miru, Office-ku, Velara, and question mark. So by using this RNN to do for translation task, we are unknowingly constraining the output to only 4 tokens. But in our case, output is 6 tokens. And this is one of the constraint, and the other constraint is grammatical structure. Grammatical structure, when you look at English grammatical structure is subject plus verb plus object. Telugu grammatical structure is subject plus object plus verb. So this combination, so these are the two drawbacks when we use RNN as it is to solve translation. Let's see what could be a solution. The solution is encoder decoder type modeling, and the other thing is connectionist temporal loss, CTC loss. So I'm not going to cover what is CTC loss here. I'll be talking about encoder decoder. Yeah, before I think before going to encoder decoder, we can stop for like 2-3 minutes here, and I can take any questions if you have.
Yeah, already they have some questions and they typed in the chat box. If possible,
Okay.
please check them.
Yeah, okay. A moment, my laptop.
It's fine, if possible, check it otherwise.
Yeah.
But then we can have it.
Yeah.
So I'll read out the question for you otherwise.
Yeah.
So can these models be used for medical images also? That's what one of the question. Let's see.
Okay. Yeah. Yeah. Medical images is not a sequence as such, but still it can be converted to sequence. Like, for example, you can split it into multiple boxes, or you can split it into multiple grids and consider one grid as first token and second grid as a second token, and so on. And then you can use it for sequence to sequence as a sequence to sequence task, and use these models. Otherwise, the general suggestion for any image modeling task is CNNs. So you can look for CNN. CNNs is nothing but convolutional neural networks. Yeah, I don't have anything on CNNs on for today's talk. So yeah.
Yeah, next question. Can the presentation be in, okay, it's a kind of, they want it to be, your presentation, they want it to be in full screen mode.
Okay, yeah, as you already know, when I keep it in full screen mode, what's happening is the lower part is being cut. So I
That's
thought
the only
maybe
reason. Yes.
Yeah.
That was
When
the
I keep
reason
it in
for
full
me.
screen. Yeah.
That's fine. Better go this way.
Yeah.
You can proceed.
Do we have any more questions? Or yeah. Okay. One.
Madam,
Yeah.
there is also one more question.
Yes, sir. Yes, sir. I'll read out.
Professor
Please
Hemant
check
Kumar.
it. Yes, sir. I'll read out. And please.
Yeah. How?
Yeah. Shall I read, or can you see the questions?
You can read me.
So one question is how to choose these models. That means, for example, text classification, we can take LSTM. That's what the question was.
Yeah. So how to choose which model? Yeah. Every model has one or the other drawbacks. So I'm going to cover them. So the latest, I would say LSTM or GRU is something that you should choose, and you should take a bidirectional, because as we have seen the problem with unidirectional RNN, where it doesn't consider the future context. So yeah, the most commonly used is bidirectional LSTM, but the problem with using bidirectional LSTM is training time will be more. What I would also want to add one more point here. There's one more technique which is called transformers, which is like that is going to come up in the talk. I think I'll take up this question in the end, because I'll be covering even more other techniques like encoder, decoder, and attention techniques as well. Yeah, should I proceed with the talk?
Yeah, one more question. So there was another question. Whether these sequences can be used for genomic data. Are RNNs are preferable for genetic sequence?
Okay, I think they can be, but I haven't worked on it, so yeah, I cannot answer that. Yeah, I think they can be.
It can be actually, because there is some sequence right in the data, so it can be used. Basically.
Yeah. Yeah, any sequential information. So these models can be used for converting any sequential form of information to other sequential form of information. Yeah, let's go into more examples.
Yeah, we'll take the questions at the end. Okay, so let's continue with the talk.
Yeah, let's go into, yeah, let's go with the talk. The problem, yeah, the problem here we saw with using RNN as it is grammatical structure formation and input, like when input and outputs are of different lengths. So by using RNN as it is, we are constraining the output to have same length as input. The solution here is encoder decoder. What is encoder decoder? Let's start with what is encoder decoder. Encoder decoder models, basically encoder is a RNN and decoder is a RNN. Let's see what happens with encoder on a simple example. Here, same Miro office ki Velara example. So here in this case, Miro is given and the output. So whatever output comes for the first token is ignored, and then the second token office key is given, and this output is also ignored. Velera is also given and the output is ignored, and the last token's output is not ignored, and the last token's output is considered as encoder's output. This complete RNN is called encoder, and this RNN takes the input sequence and the final output is considered as encoder's output. Now let us see what is decoder. So decoder is another RNN. Our decoder also takes start symbol as a first input and encoder output as another input. The intuition here is that the encoder output actually encodes the complete input. So it has the meaning, it has the complete meaning of the input, and it is used to give the, yeah, this encoder output is given to the decoder, and the start symbol is also given to the decoder. It the first the first thing it predicts is did, the first word. So when you give the start symbol, we are saying decoder to predict the first word, which will be did, and for the second iteration, the first prediction is given as input, which will be did, and also the encoder's output is also given as input, and prediction will be u, and for the third, u is given as input and encoder's output, and go will be the output, and so on till the end. In the end, we get the stop symbol where decoder will stop decoding. So once we have the decoded output, we show it. So this is decoder. So this kind of models where you encode the complete input into say single embedding and then use decoder to decode the encoder's output is called encoder decoder type of models. Here we can use RNNs, and there are other techniques like transformers. Yeah, let's go into details. So after encoder decoder models have been published, even then people have seen some haven't seen much improvement in the performance. There is still scope for improvement. So then there is this question: what could be going wrong? What are we losing something? So the question comes, are we losing this information? Is this information important? Then to answer this question, let's yeah, can we do something here? Let's analyze more into the input and output. We have input మీరు office కి వెళ్ళారా, and output did you go to office. Let's analyze which token depends on which input. Yeah, if you see did is a verb, right? It is a verb in past. So vellara, did mostly depends on input word vellara. So when you see the prediction of you corresponds to miru. So the prediction of you mostly depends on miru. Then if you see the next word go maps mostly to the vellara. And if you see two maps to like office ku, and office obviously maps to office, and question mark is more dependent on question mark. So here if we see the prediction of each word is like when you are predicting a particular word, the dependency on input is different. When you are predicting office, the input token office is more important when you are predicting office. When you are predicting go, input token velara is more important when you are predicting go. When you are predicting you, input token miru is very important when you are predicting you. So this is called attention. Basically whenever you are predicting an output, on which input tokens do you want to attend more, do you want to show high attention. So this technique is called attention. So in this technique what we do is, when you are predicting a particular output, you give corresponding weightages to the input. So when let us try to apply this particular technique on encoder decoder output. So instead of ignoring this output, let us try to use them all. So output 0 which corresponds to miru, output 1 which corresponds to office ku, output 2 which corresponds to velara, and output 3 which corresponds to question mark. So what we do here is we take a weighted average which we call as a context. So these weights are called as attention weights, and the way of taking this weighted average is called applying attention. So once we take this weighted average, we give it to the decoder. So when you are trying to predict D, you give high weightage to output 2 which corresponds to velara. When you are predicting you give high weightage to output 0 which corresponds to miru. When you are predicting go, you give high weightage to velara, which the output 2 which corresponds to velara, and so on. So now the question would be, what does this attention weights depend on? So my answer here would be, yeah, these attention weights depend on the corresponding decoder input. But in this talk, I will not be covering those 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 things. Yeah, let's move ahead. So, yeah, let's now look back. Yeah, did we get the intuitive understanding of how sequence to sequence modeling works? And yeah, did we understand? Did now do we have high level answers to the questions? What is sequence to sequence task? How is sequence to sequence task modeled, and what is DNN? How is DNN modeled, and what is RNN? Why do we need RNN? What is bidirectional RNN? What is encoder decoder model, and what is attention? I think I have covered all these things which I told in the beginning of the talk. So yeah, I think I have come to the end of my talk. Yeah, what next? Next comes something called self-attention. Self-attention is nothing but you are. Yeah, I'll not be covering self. Yeah, these things can be covered in the next talk. Self-attention and transformers are current talk of the town in sequence-to-sequence modeling. So if you take any state-of-the-art models, even Google Translate or any state-of-the-art sequence-to-sequence model uses self-attention and transformers. And so if you are interested in this, you can look for attention is you can look for papers, attention is all you need. And there's another paper, LSTM, there's another talk where the title is LSTM is dead, long live transformers. So yeah, I'm not covering this attention, self-attention and transformers in this talk. Yeah, that's all. I think the talk has finished very early.
So now, shall we take questions from the audience?
Yeah, yeah.
So dear participants, if you have any questions, so you can unmute yourself and you can ask them, or otherwise you can type your questions in the chat box. I'll read out for you. So I think it's fine. So I think there is a question, sir, how Google Lens recognize the text of so many languages and text in different color and different font? It's a nice question.
Yeah, yeah. That
From
that comes.
Vamsi.
Yeah, that comes under OCR. So the first thing that happens with Google Lens is it it the first thing that happens is image processing, because anything that you look from a lens is image. So that image is processed and we get text out of it. So once we get the text, we process it. So that technique is called OCR, I think. So I haven't worked on it, but you can look for it.
So there is a question from Hemant Kumar Gadi. Nice presentation, sir. You have given very high level view of the model. So next time, please take up any model in detail, sir. So it was
Yeah.
a kind of note. Then Commercials Ram Kumar. So there is a question. Are there any differences while modeling speech to text and text to speech? If yes, what are the differences? Please explain.
Yeah, there are differences. So in speech, when it comes to speech to text, the input is speech. So as I have told you, uh, speech is processed like this. So every 25 milliseconds, and we take the embeddings, and then we give it to sequence model, and the final mapping is in, which is a slide that explains this. Yeah. So yeah, input is when input is voice, it is converted to sequence of vectors and given to the model, and similarly we get the output. So yeah, it's very generic. To go in details, I don't have any specific slides to explain in detail the difference, but the overall view is both are sequence to sequence models, and this is what happens inside. Maybe, yeah.
Yeah, there is another question from Hemant Kumar Gadi. How Google team compete with OpenAI and GPT models?
Yeah, yeah. The latest talk of the town in NLP is GPT-3 model. Google has released T5. So first thing I want to tell here is that I am not representing Google here, but so whatever I say, I mean, I'm not right person to talk about it, but still I know that there's this model called T5, which is a text to text model. So yeah, T5 is one of the model which is kind of as giant as GPT model, and also is giving similar performance as GPT.
Next, another question from Ram Kumar. In industry, we have tried to implement speech to text, but it is still at a very nascent stage with 65% accuracy. So I used Google Translate APIs, whereas text to speech was 99% accurate.
Um, I, I think I can add anything here. Yeah, it is a suggestion. It's an information. So yeah, there's another question on LSTM is dead. Yeah, it's not exactly dead. It's a title. It is a like interesting title to acquire the audience. So when they say LSTM is dead, they meant to say that transform. If you use a transformer instead of LSTM, you'll always almost get good results. So there is a very nice talk in YouTube with the same title, LSTM instead and long-lived transformers. So there are some drawbacks with transformers as well, because I didn't cover what transformers is in this talk. Maybe if I say what, like, drawbacks in the sense it cannot transformers cannot handle longer sequences, and also it takes a lot of memory and computation. So one of the benefit with transformers is it does a lot of parallel computation. Everything is parallelized. Yeah, there are drawbacks and there are benefits, so it depends on your specific task. It depends on your task. When you know that your input won't be longer than say 512 tokens, and when you know that your output also won't be longer than 512 tokens, you can straightforward go and use transformers. But when you're not sure that your input can be of any arbitrary length, like 2000 or 10,000 tokens, then transformers is not the thing that you're supposed to use. So then LSTMs might be the thing that you might want to try. So it is very use case specific choice. So any model, whatever model you take, it has some benefits and some drawbacks.
So there is a request for sharing the PPT. So for some reasons, we'll not be sharing the PPT to the participants. So if you have any other questions, no, please feel free to raise your questions. There is a question from Lokaya Lagura. So LSTM gives better accuracy in prediction than transformers. Does LSTM gives better accuracy in prediction than transformers?
I would say, I mean, not in general, but there are cases. So yeah, they are not in top of my mind as of now, but yeah, generally it is considered transformer performs better than LSTM. The main reason is transformer uses attention. So after attention is all you need, paper is released in 2017. So every research work like everybody started using attention, and they have seen a lot of improvement. And transformer is nothing but an architecture which only uses attention. So generally, transformer is considered as a better model than LSTM.
So, any other questions from the audience? So they're asking you to share your work experience. That means how you tackle any kind of problem, how to start from scratch.
Okay, yeah. This I can share. So yeah, given any problem, for example, let us say we want to do the translation task itself, or let us consider audio visual speech recognition. So like there is this task where you want to develop an app where you want to do audio visual speech recognition, so, which captures audio and video and converts it to text. So when such problem is given to us, like how I'm only sharing how I try to solve the problem. So the first thing is we look for has this been problem already attempted by other people, and what are their approaches. The first thing is first 2 to 3 weeks we try to spend time on literature survey. We try to find all the articles that talk about the specific problem we are trying to solve, and we try to, so as a team what we do is we distribute our work. So each person is supposed to look at specific set of articles and come up with a summary, and we meet after a week or two, and we'll have a meeting and each of us share our understanding of what we have read about. Then once we have complete understanding of what work has been done, then we look at can we utilize any of the work as it is, or do we and yeah, we then try to prioritize which work we can utilize or which direction we should go. Then we will also look into um, can we improve it, or also we'll also look into should we talk to uh, some other academicians or like any professors to get more insights. So that is also another direction we look at. So once we have also one of the important thing in being industry is you will have to come up with product, so there's no option for you. So like you'll also look at you should also look at how can you launch this project, so the memory requirements and the runtime latency, can you put it on the server or will it be on device? So this is another constraint that we look at. So if there is a model, if there is a model like GPT-3 and all, so you can't launch it, or like it's so huge that even its inference time is so high that you can't actually launch it on device. So what we look at is even if we trade or trade like even if we lose on some accuracy, it's okay, but we want the end of the day, if we are not launching it and we are not launching it doesn't help us. So we'll even if we lose on some accuracy, we take the models that are launchable and work on it.
So if any one of you would like to ask any more questions, they can ask, or you can even share your feedback on the talk.
Yeah.
So you yourself can unmute and speak actually. So shall we wind up the session then? So, seq. Sir, HOD sir.
Yeah, madam. Sorry,
Sir,
sorry.
sir,
I got a phone call. Okay.
sir,
Yeah.
no problem, sir.
So
Sir,
done, madam?
yes, sir. Yes, sir.
So
So can you
yeah,
share your views?
yeah. Thank you, Dilip. It's a nice presentation. It's a translation of English into a Telugu, and I think that may be possible for other Indian languages also. Maybe that becomes a reality over a period of time. So see, it's very good actually to see this the various deep neural network models, that RNN and other models, and how the translation will happen actually from one language to another language. It's very good to understand, explain in such a way that the people like me also could understand, because I don't have much background on machine learning and the neural networks. So I used to learn from our faculty members, so it's a very good presentation, and I hope the session is very, very interactive. I think this is very much encourageable, and in the future webinars also, I request all the participants to interact. So only when you start interacting, then only we can learn relevant things from the experts. Otherwise, if we don't question ourselves, we cannot learn anything actually. So I'm very happy to see that there is a very good interaction from all the participants, and I've been seeing the messages which contains their happiness actually, especially on this particular the webinar, and they are expressing their gratitude to the speaker in very good words. So thank you very much, Dilip Kumar Garu. So I'm sure that we'll be in touch with you for future webinars also. I hope you will support the webinars that are going to come in future. So I heard you are also alumni from IIT, the Madras. So it is good to see. Yeah, so I'm also an alumni of this IIT Madras, so it's good. So this is how people of alumni of IIT is contributing for the growth of our society. So we should feel pride about as alumni of this IITs and how the alumni are serving for the country. Thank you very much. Thank you.
Thank you, sir. Thank you very much. It's my honor, and yeah, it's my honor to be and give the talk.
Yeah. Thank you, sir. Dilip, there is another question. Maybe you try to answer that. So what would you suggest or advise for a fresher who are coming into data science without any coding experience? Like they want you to share kind of websites, books that you can suggest.
Okay, so coming to data science, first thing I would say is there's not much coding, but definitely you should know the basics of coding. So mainly why I'm saying there's not much coding is everything, like all the difficult things are already coded as a library. So all you need to do is include them and call them. So if you can handle that, like most of the machine learning work is done in Python. So if you can do that, uh, yeah, you don't need much of the coding experience when it comes to coding experience. And so when it comes to building applications, I would say you might not need much. One of the basic thing that you need is statistical mathematics, right? In mathematics, probability and linear algebra are the two things. So probability, which comes under statistics, and linear algebra are two things that I would say these are the two languages that machine learning speaks in. So everything in machine learning is spoken in terms of linear algebra or probability. And if you are interested in understanding the mathematical details, these are the two things that you should look at. And if you're not really interested in maths and still want to do something, yeah, there are many blogs outside on how to start on machine learning. Like even without all this mathematical knowledge, you can think of machine learning as a black box, a simple black box where you do hash include like for example transformer. So if you want to implement transformer, you have to do hash include transformer and transformer dot fit and give your data. So it has become so simple, but the I would say the main problem here is because the confidence you'll have when you also know this maths and coding is different. So when people know maths and coding, they look more confident. But I would say even without that, you can do a lot of things. And in the process of doing the things, you also need to and understand maths.
So they're asking you to suggest a book on NLP.
Okay. There's no specific book I have followed. So I did follow my professor's lectures. So that is one of the main things. So I can get back to you. So I can find out and get back. So when it comes to me, I didn't follow any specific book.
So you can check the feedbacks in the chat box actually. So people are kind of very much connected to your presentation and they're sharing their thanks to you. So
Yeah, thank you.
we'll close with the closing remarks of the webinar. So thank you, Mr. Dilip Kumar Markham, for sharing your knowledge without holding it back with you. So it was really an interesting presentation. So one thing is it's kind of a challenging task to deliver lectures, these kind of complex lectures, so the recent advancements. So especially when you are dealing with audience with multiple levels, like here we have students, then faculty, even they are having very little knowledge on machine learning or the deep learning. Then we also have certain group of people who are actively working on these problems. So dealing with all these set of people, no, it's really challenging. But you did a reasonably good job. So we feel all the participants enjoyed your session. So I hope this lecture generates more interest in sequence-to-sequence learning tasks and sequence-to-sequence learning models, and inspires the participants to work towards these kind of models with renewed vigor. So on behalf of the organizing committee, I thank all the participants for joining this webinar. I hope the webinar served its purpose to the extent possible. So we are extremely thankful to our chairman, Dr. Lau Rataya Garu, who always motivates us and supports us to organize these kind of events. I thank Dr. M.Y.S. Prasad Garu, Honorable Vice Chancellor of VFSTR, Dr. Raghunathan, Registrar, VFSTR, for providing all the support that is required to organize these events. And I also would like to extend my special thanks to Mr. Dilip Kumar Margam, so taking up this challenging job and accepting, so I just requested him for a talk. So he immediately accepted it, though he was very busy with the interviews, so he is part of the recruitment team and all. So even then he accepted our request with a short span of notice. Thank you, Dilip, once again for accepting our invitation and for delivering such a wonderful lecture to our faculty and students. So I thank Dr. D. Venkateslu, HOD CSE, VFSTR, for the enormous support he provided. So, sir, without your support, these kind of webinars wouldn't be possible. I thank all the faculty colleagues who actively involved in organizing this event. Once again, I thank all the participants of this webinar. So soon, of course, feedback form is not yet being shared. We'll share the feedback form soon in the WhatsApp group. So Dilip, would you like to talk anything?
Yeah, I would like to say thank you to each one of you who are present here, and thank you for you, Josna ma'am, for asking me for giving this presentation. Otherwise, I wouldn't have been motivated to take up such tasks. And I would also want to say thank you to all the research community for sharing the knowledge with us, and all my past professors, like professors at IIT Madras who had taught me. And yeah, thank you. Also, I want to add the suggestion about the suggestion about what book to follow, right, for NLP. So one thing that I regularly follow is r/machine learning in Reddit. So it is a subreddit thread. So all the latest updates in machine learning and NLP come up in Reddit. That is one thing that I look at every day. So if you are interested, I would say you should start following r/machine learning subreddit in Reddit.
Okay, I'll share you the link. So that would be better. So
yeah.
Thank you. So anything else would you like to share? So it's better to give your feedback, oral feedback, to the speaker. If any one of you would like to. So we close the meeting then. So if there is nothing to share, then I'll close the session.
Madam,
Sir?
Josna madam.
Sir, please.
Better to have a photograph, madam.
Yeah, thank you. Thanks for reminding. So I actually forgot. So can you open, all of you, your videos? We'll take a photograph. So please open your videos so that we can
Dilip, you
take a
can
picture.
stop your sharing. Stop sharing the slide, please.
That's fine. I just minimized it. That will not be a problem. So
okay.
Still I can take. So those who are wearing masks, they better remove so that you will be visible. Your face will be visible. So ready? We'll take the screenshots. Others also can open actually. So only very few people open. Less than 20. So there are around 70, more than 70. Guys, please open your videos, your cams. So the speaker has shared a link of Reddit. So those who have asked for NLP's book, so they please notice that. And even I will share this in the WhatsApp group so that everyone can get this. Thank you all. So thanks for participating in this webinar. Thank you.
Thank you, madam.
Thank you, sir.
Thank you, Dilip.
Thank you, sir.
Thank you, madam.
Thank you, sir. Thank you, Dilip, once again. Thank you very much.
Thank you, ma'am.
Thank you all. I'm closing the session. Thank you.